Hi. Race lysine faux sizzle. Faux shizzle. I have Brad Anderson to thank for that one, and apparently Qbert as well. I've no idea what it means, but it seems like a good thing. These got lots of great features in it. Lots and lots of great features. I think race lysine is one of the better ones because it allows you to do things real fast, where in some other languages, you just don't have that opportunity. So I'm going to try and explain to you where it can be used, how it can be used, what some of the benefits are. Of course, it's not a magic bullet. You can only use it in certain environments or for certain types of things. But when you do use it, it can be very, very effective. And I hope to be able to show you how that happens. Okay. So before I do that, I want to give you a little bit of background about why I think they're so great. Because I do. And I think perhaps to do that, I need a prop. I need a phone. Do you have a phone? Thanks. All right, back in 2001, I was working with a company who were doing some high transaction throughput using web servers and so on. They had an interesting application. They were building gambling applications that you could use on, phone kind of device. And the idea would be that you would go along to a track event or not, just sit in your home or whatever and sit with your phone and bet on the horses or the dogs or whatever it happens to be. And the way that this operates, the way that it did operate back then, was that people have a general idea about, which dog it is they want to back, or which horse. And so they go through a series of, little screens to get them where they want to be, and they make their selections, and they don't actually post their bet until the odds are in their favor. So once as it comes up to post time for the race to get started, the user is sitting there. They've made whatever selections they're going to make, and then they sit there for the next 5 minutes right before the race starts, and they refresh the odds page and refresh the odds page, waiting until the odds on their choice is in their best benefit or best interest. And so you can imagine that with 1,000 people using this at a racetrack, or a couple of thousand, whatever, and then you multiply that by the number of racetracks across the United States or whatever, it's a lot of people going, give me the odds page. And as it gets closer to post time, you can imagine the anxiety level builds up a little more, and they're going, So response was really, really important for this application. And of course, number of requests ramps up until right at post, about 3 seconds before the race actually starts, everybody goes, transact! And the system has to be able to deal with it. And this is a problem. As you can imagine, right? So we were building this stuff with Java. Okay. I heard a snort of derision there. Gambling time. So it's interesting. I mean, Java has a reputation for being slow. Okay. So we went through and we tried a number of different web servers. We tried, Tomcat, of course. We tried that first off. And the way we tested these web servers was to give them a hello world program, or a hello world page to send back. And we hooked up a whole bunch of clients to the server, and we beat the crap out of the server. Right? And Tomcat managed to get an astonishing, this is back in 2001, the machines we were using were like 866 megahertz Pentium 3s with a gig of RAM or something like that. I mean, they were fast in 2001. Commercial systems, of course. So we'd stack up a bunch of client simulators around the side that were just going to say, give me a transact, or give me the odds page. And the server would just send back hello world. So yeah, Tomcat managed to do an astonishing 110 requests per second or something. It really wasn't in the ballpark of what we were hoping for. So then tried resin, capture resin. It's a great product. It has lots of great functionality, great facilities, IP redirection under the covers and all kinds of stuff. It's very, very cool. And it got us up to about 550 requests a second, which is, it's not to be sniffed at. We tried WebLogic. I think WebLogic was 5.0 or 5.1 or something at that point. And we tried that, and it got us up to 600. And we're going, maybe, So one weekend, I wrote an HTTP server, thinking, we've got to be able to do better than this. And it did everything that all of the other ones do, I think. I mean, it did all the usual stuff, the headers and the whatever, all the good stuff, cookies and so on that everybody else does. And yet, it was a whole lot faster. And the reason it was a whole lot faster was because it did very, very little memory allocation. It was a whole lot faster. In fact, we used to sit around at nights for the next week or whatever, carefully and painstakingly going through all of the code and removing the last string concatenation where we didn't need it, And we got the thing up to 1,600 requests a second. I mean, this isn't Java. It's still pretty reasonable. So, at that point, I decided that Java really wasn't slow, that it was the use of or perhaps overuse of the garbage collection, or the garbage collector, that was the issue. At least that was my feeling at the time. All right, so that's one story. Now the other one, in 2000, well, of course, that company, this is right at the back end of the dot-com boom, and that company tanked. It went down like a lead balloon, and that was a lot of fun. In 2002, I got asked to come in and do some troubleshooting in an application, another company in the Valley. They had a client-server type application, and it was distributing, pages and so on to people. So the pages were quite complex, but the server was having some difficulties. Some of the pages were taking 30 seconds to return to the user, for example. It was a major issue, and they were supposed to respond like this, but they just wouldn't. So the other problem it has was that it was running on a big piece of iron from Sun. It was like a Sunfire something or other, whatever. And this is like 2002, and it would get to about 14 users, and it would just stop working. The whole app would just stop. You wouldn't get a page at all, let alone 30 seconds. So this was a little detrimental to the ability of the app to sell itself. And the salesmen were incredibly good. So anyway, so they asked me to come in and see if I could point out some issues. So we instrumented the application, instrumented the server, and took a look at it. Some great instrumentation tools in Java, by the way. I mean, really, just great tools. I think that one was from Borland or somebody, but it was awesome. And the first thing that I noticed at that time was that before the server had even got to the point where it could serve pages, it took a very, very long time to get there, even on an 8 CPU box with gigs of memory. The instrumentation was telling me that it had allocated and disposed of, the garbage collector had actually managed to collect, over 4 gigabytes of memory. And this is in 2002, So I call that one a bull in a china shop, because it was just out of control. I mean, some of the problems got rectified and so on. But the upshot of that, I think, thanks for the phone. The upshot of that is that garbage collector abuse can really, really hurt. And so I'd like to take a look at some of the things that D may be able to help with in that direction, using array slicing and so on. But yeah, overt GC reliance. I'm going to talk this out because this is an important one to me. Overt GC reliance has the potential to make any language or system appear sluggish. If you beat the crap out of it, you're going to have a hard time on the back end as well. Of course, Java didn't really have things like structs and array slicing or free lists per se. I mean, you could build those things into it, but it really wasn't very natural, and so people didn't tend to use them. You just create. If you create a vector and you add things to it, for example, you're allocating memory all over the place. You're concatenating strings. You're allocating more memory, and there's just more work, more things for the garbage collector to keep track of, and more work for it to do on the back end. Lots of stuff like that. Because of that, then the libraries written in Java, they tended to be fairly GC heavy themselves. So if you're using a library, you're not getting any thinning effect out of it, if you like. It's not just in the application, in your application that you're writing you have to worry about. It's all the libraries, whatever. And the two applications the web server type thing and the bull in the China shop, they're great examples of people going overboard. String concatenation, of course, I mentioned in Java. It's not a huge issue, really. I mean, it can be dealt with things like string builders and so on, but people are lazy. They just concatenate strings together. You see it all over the code. Another example that Scott mentioned to me earlier today was that if there's one thing worse than string concatenation, it is DOM concatenation. And that's what was going on inside the bull in the China shop. There were DOMs up the wazoo, and they were all being merged together for every request. Thank you. So the other issue, of course, is that if you're in a multi-threaded environment, many of the garbage collectors available today, they will synchronize every thread. So as each thread is making as each thread is making a request on the heap, you're going to get a mutex involved, and threads are going to be beating each other out, trying to allocate memory. And of course, the GC collector and a mark and sweep will stop them all as well. It's a stop the world type of collector as well. Nowadays, in commercial devices coming out now, the Sun Niagara T2 is capable of executing 64 threads concurrently. The Tylera device that was announced the other day, it's a 64 thread device as well. I mean, there are commercial devices out now. Multi-thread stuff is going mainstream. And you don't want 64 threads stopping each other just because they're trying to allocate some memory, and you don't want the garbage collector stopping 64 threads every time it makes a collection. There are ways around that, of course, as has been pointed out. Of course, you just make multiple processes instead of doing multiple threads, but of course threads have some benefits that we all know and love. So the enigma in that is that Java still flourished on the server, despite the issues that it is very, very heavy on the garbage collector, or can be. If you're careful, you can work around it. But it flourished on the server, and it did a great job, because when it comes right down to it, Java is a very safe language to program in. You write it, it compiles, and the damn thing works. It's amazing. From a managerial level, it's fantastic. It's a godsend. Code just works. Brilliant. So, moving on. So there's a number of different ways that you can reduce the pressure on the GC, and you're familiar with a few of them at the top there. Of course, C++ does all of these. You can emulate some of them in other languages too, like Java, for example. In that particular one, I've rarely seen it used. However, array slicing is what this is all about. And array slicing is where D adds a little bit on top, just a bit of icing on top of the cake, which I think is great. All right. So what is it? Array slicing is array aliasing. It doesn't allocate anything new. It just gives you a little window on an pre-existing piece of data, and then this sort of here. This is a chunk of memory. It's supposed to be a chunk of memory down here, the red piece, and that's referenced by array here. And then I'm taking a slice of it here. I'm indicating a start point and an end point, and that's giving me this little slice right there. And what you get back from a slice is actually an array. So you can take a slice of a slice of a slice of a slice of a slice. And they're all pointing, ultimately, to a segment or a section within the original array. If you change the contents of the original array, your slices are going to change too. So it's not a freebie, obviously, but there are some environments, such as read-mostly environments, where it's very, very useful. All right. I've got so many things to play with now, I'm not sure which one to press. So to take a look at array slicing, I want to walk through 3 different kinds of examples. The first one is text processing. A sliced HTTP server, which is similar to the one that I talked about in the introduction. And then a clustering, doing some clustering with this thing called Tina. Tina is not my girlfriend. You can't go and cluster with my girlfriend. But it's a nice name for a piece of code. So we're going to go straight into text processing. Now, I hope you can see all this. I thought doing a dark background with white text would show up really nice on a projector, but I was wrong, so forgive me. All right, so we have an example up here. This is taking an integer, or actually an unsigned integer up here, and it is returning a character array of the output. The important part here to take a look at is that there's an optional second argument where you can provide where the output should go. And I say it's optional because you may want to just, send the contents out to a temporary place on the stack, convert it onto the stack and then grab what the actual conversion was and do something else with it, Or you may actually want to allocate it on the heap because you're going to stuff it into a hash table or something, whatever. So this little routine handles both of that, and it does it through the use of array slicing. Right at the bottom here, we return a slice of what the output that was given to us. Now, the reason we return a slice is that you pass an integer over. It could potentially be 10 digits long, or it could be 15 digits, or whatever. 2 digits, 1 digit long. So you don't want to, pass back the whole thing. You just want to pass back the valid number of digits. So D has this really nice thing, whereby you can test the output buffer to see if it has enough room in it. And at this point, I'm using something here that's not actually supported in D, which is perhaps why Walter was looking at it going, huh? That there says uint.dig, and .dig is a property on the floating point type, not on an integer type, and .dig returns the maximum number of digits for a floating point type. And it'd be nice if we could get something like that for integer types also, to say this is the maximum number of digits you'll ever have to deal with. Okay. So, all right, so here I'm checking output.length if it's less than, let's say, 10 for unsigned integer. Oh, units. Sorry, I beg your pardon. Yes, that wouldn't compile. Right. This isn't actually a piece of compiled piece of code. I just wrote it in PowerPoint, so forgive my. Yes. So the upshot is that if the length of the provided array is less than what we're going to use, then I want to reassign the length of the output array to be what I potentially need to use. Right? This is trivial stuff, right? But the interesting thing is that if you pass a null over here, this test will take, and we reassign the length here, but this puts it on the heap, which is nice for default behavior. It's great. It stuffs it on the heap instead. All right. So we're going to use the heap in that example. If the user actually passed a buffer over here that was, some buffer on the stack, and there's at least 10 characters in it, we don't reassign, so we use the stack instead. If the user had provided an output buffer that was also on the heap somewhere, and it also was at least 10 characters long, great, we'll use that. If any of those conditions fail, then it will allocate. And the other nice thing about D, at the end here, when we return a slice of the output, you notice that we're returning just the number of valid characters in here that we actually managed to convert. If we return a slice that points onto the heap, the garbage collector knows about it. So we don't have to pass the head of the heap allocation back to the program, which then hangs onto it. You can pass a slice back to the program, which hangs onto the slice, and the GC still sees it as being used. This is a nice thing. So the upshot, anyway, is the body in here. The body does very little, of course. It just does you convert an integer into text. No big deal. But for such a small routine, there's a lot of good stuff going on inside there in terms of slicing. Any questions, just please stop me as I'm going through. UTF conversion. Converting from UTF-8 to UTF-32, for example. A similar kind of process going on. You know, you've got this one's converting a character array to a double wide from 8-bit UTF to 32-bit UTF. And we're also doing the same sort of thing here. We're giving them the option of an output buffer. So you can convert it on the stack. If you think you have enough room in your stack buffer to convert the input string, then go ahead, pass the stack buffer over to it. It'll convert it in place in the stack buffer, and it'll give you a slice back, a valid slice back of the stack-oriented buffer. If it turns out that the UTF conversion routine thinks that the output buffer is too small, it'll resize it as appropriate and put it on the heap instead. So it's just a nice little escape mechanism that works very well for trivial use, and then it also works very well for those people who are concerned about performance. Yeah. So similar kind of thing as the previous one. The third example for text processing that I'd like to show you is split lines. Two variations of split lines. Split lines is something that, of course, it takes a look at a piece of text and goes, okay, there's a character turn there, there's one there, and there's one there. Here's all the pieces back to you, blah, blah, blah. And then for each is a D idiom that allows you to iterate over each of those things. Now, there's a traditional way of doing that, and there's a D way of doing that, I suppose, or a non-traditional way of doing it. The traditional way is to take the text, which is over here on the side, 3 chunks of text here. You take the text and you create a little array for them, and you isolate each piece of text individually. You put the bits of text on the heap. You copy the reference from the heap into your little array with 3 entries in it, and you hand that array back to the user. And in this particular case, this actually returns an array of character arrays. And the for each knows to iterate over each of those. Yeah. That's fine, and for trivial use, I mean, who really cares? I mean, that's great. Yeah. If you're doing a lot of text processing and a lot of line processing, you probably really want to avoid the garbage collector overhead or the heap overhead or whatever. You don't want to put too much pressure on the garbage collector because it really is a tool. So the other option in D, which is this one down here, avoids all heap allocation and thus avoids all GC pressure. And the way it does it, it uses an up apply. I hope you can see that. It's kind of a little dull. So the for each is iterating for each line. It's exposing a line for each of the elements that are here. Now, the interesting thing about this particular function is different from the split lines above it, from the traditional split lines. What this one does, it actually returns a structure which has an up apply in it. So it takes the myText pointer, it stuffs it into a structure. The structure of the struct has an up apply function so that the for each can work with it. And as for each then calls the up apply inside the struct goes, oh, here you go, here you go, here you go. Right, just slices the content through. Thank you.
On the website is the word count benchmark. The word count benchmark does no memory allocation, it just does slicing. And it's great, but it completely blows away C++ because C++ does explicit memory allocation and deallocation. And a lot of people have accused me of all kinds of sabotaging C++ and stuff like that. But interestingly, it's an example of why garbage collection makes your program run fast, because with slicing, you don't have to do any garbage collection.
Right.
You don't have to, because the fastest memory allocation is no allocation. And garbage collection, even though benchmarking garbage collection will show it to be slower if you match it malloc for new, it will be slower, but it's faster overall because it enables you to do a lot fewer
Good point. So, I mean, this is all very well if you're not going to be making the resultant lines persistent in your program. If they're just, oh, okay, they're temporal. You know, you just take them, you do some processing, and then you move on. Right, so slicing is fantastic for that kind of thing. If you really need to take them and stuff them in a hash table or something, then you can still use this particular version, but you do a line.dupe, which of course would stuff it on the heap or whatever at that point. Having a function like this allows you the option to have, it gives you two options. You can take it the fast way, the streamlined way, what I like to call the fast path, or you can, take the more traditional path here, which is more convenient and it's more dependable, I suppose some people would say. You don't have to think about it if you just stuff it on the heap and let the garbage collector deal with it. I like to have a fast path. When I build application level things, I like to have a fast path through it. It's like drawing a vector all the way through the application and say, hey, this is the quick way to get through it, and anything else is icing. You can sort of add little bits and pieces along the vector to say, okay, so we'll have some nice functionality here and there. But the fast path is a useful notion to me for that. And this gives me a fast path, this type of approach.
That's the rate of spaceballs mainly.
Thank you. Let me change that right now. Okay. So the second example I'd like to use is a sliced HTTP server. And it's sliced because it does no heap allocation when it's running. It does a little bit of upfront heap allocation to get things jump-started, but after that point, it doesn't allocate anything. So it's basically heap-free. And as Walter pointed out, that is the fastest way to make things work. You just get rid of the pieces that potentially slow you down. So you have a client here, it makes a request. The request goes over to the server. The server sees this box over here as structured data, because of course it needs to be able to extract out the various bits of each of the requests. It needs to know, is this a put or post or a get or whatever. It needs to know what version it is. All of that needs to be parsed out from the request. The URI needs to be broken down into its constituent parts to get the path and da-da-da-da-da. So all of that needs to be broken out. The headers, of course, need to be broken up into, here's a header here, and here's its value, and da-da-da. And there's a whole ream of those, and they're in an array or some kind of structured environment that the server can dig them out, or that the applications running on the server can dig them out. And the same with cookies and so on. So in a lot of HTTP servers, these things tend to get allocated on the heap. You parse through them, and each component piece of the request get allocated on the heap, and they're there for the application to say, oh, yeah, okay, well, I'll take a look at that. A lot of times the application doesn't even look at the pieces of it. Like some parts of the URI. I mean, most things don't even look at the scheme in the URI. For example, most servlets wouldn't look at the scheme. So it just gets allocated on the heap, and it's not even used. I mean, I think that's criminal. So with this particular approach, or what this particular server does, it doesn't allocate any of this. It just slices it. I mean, what happens is that the input coming in from the client sweeps out into a buffer, into an array, basically. And then as you parse through, it goes, oh, ding, ching, 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 all the way along. And you wind up with a whole bunch of structured slice references instead of structured heap references. Now, of course, the structures themselves, like there are some arrays that have to be allocated. So, for example, there's an array of headers available that you can traverse to get all the headers that are in there. However, those arrays are on a free list. So you fall back onto the more usual or traditional ways of avoiding heap allocation. So between a combination of slicing and free lists, this particular HTTP server, you send it a request, it can send it back, zero heap activity at all. That's great. It makes it fast. It makes it do thousands and thousands and thousands of requests per second, way, way, way beyond what the Java one did back when. So that's as an example, it stands quite well. Same sort of thing happens on the way back. On the response, of course, everything just gets stuffed out into a buffer. When the servlet or the application on the server is going, okay, here's another header to write out, and here's something else, they're actually being written out into a buffer, and they're not being written off to the heap and then taken from the heap and stuffed out into a buffer and built back up again. They're stuffed right into a buffer, and the references are maintained in free lists and as slices, and that ends up going back to the client. Now, the client may actually wish to retain the headers and retain the cookies and whatever after that point. That's up to the client to do that. Or it can be viewed as being up to the client to do that. As long as there's an ability to do it cheaply under the covers and efficiently under the covers without incurring too much overhead, then it seems like a reasonably good way to do it. And the client can just say, oh, give me all the headers, or give me a copy of all the headers. And if you ask for a copy, then great. It'll put them all in the heap for you, and then you can hang on to them until the end of your program. All right, so that's that one. I missed one. Just a second. I want to skip back. To this. Going back to the lines of text, using the same sort of notion of slicing text. Can you imagine an XML parser? XML parser is ripping through loads of entities and tags and elements and attributes and whatever. Right? A lot of XML parsers will actually take each of those pieces and allocate a chunk of memory for each of them. Right? And you're ripping through big XML documents. People have XML documents now that are like a gigabyte. That's a lot of stuff to be allocating on the heap, especially if the application is actually streaming the XML as opposed to building a DOM or whatever it happens to be. One of the interesting things about XML, even when it comes to DOM, is that if you can manage to get the entire XML document, all of it, into an array at one time, then you can slice away to your heart's content. Every reference to the XML can just refer straight back to the original big chunk of all of the content. There's absolutely no reason to go ahead and hit the heap at all in that kind of environment. So you can have all of your attributes, all of your elements, and blah blah blah, all of it, just references to this one big buffer. It's a great way to do it. I mean, some people won't do that because you want to be able to incrementally pull bits of the text as it comes in from a socket, for example. You don't have the whole thing at once, and sometimes it's actually faster overall to process as it comes in. However, for those situations where that's not the case, it's a really good idea to use slicing there instead. Okay. I already sort of talked about this one. Okay, so going back to the HTTP server thing. What actually happens, of course, is that the client is up here somewhere, or maybe over here somewhere. It makes a request to the server. It has a whole bunch of headers and URI and whatever coming in here. The server goes, okay, I've got a socket request coming in, allocates it or assigns the request to one of the available threads. The available threads each have their own copy of an input buffer, pre-allocated. You know how it works. Pre-allocate stuff, assign it to the thread. And so the request comes in, it just gets parsed straight into the pre-allocated memory. All the references are done, bang, goes straight through to the servlet or whatever it is that the client has targeted, and the rest of it comes back through. So you get a round sort of circle, or your round trip going on here, flying through, going through each of these threads, and none of them are allocating memory. That makes for a very, very efficient server, and primarily due to slicing. It's a very, very effective way to build servers in particular. And you don't need to do this, of course, or you may not need to do this inside like a word processing document or application, or maybe some banking application. You may not need to do anything like this, but The point is that it's there if you need to use it. And because it is there as a native piece of the D language and not as some additional piece that's bolted on the side, it's easy to use. That's really the beauty, I think, of slicing in D, is that it's actually a native construct. You can build this kind of thing in C++, you can build it in Java, you can build it in Python. You can build slicing in each of these things. Yes?
It's just occurring to me that in C++, an analog would be a substring as opposed to a string.
Right.
A substring is a reference to a string, but with bounds.
Okay.
But people don't write utilities that take substrings as arguments or pass substrings as results. They use strings, so you've got all that allocation that's going on.
Right.
If you do any writings.
Right, that's a good point. Yeah, it's just more convenient to use. Right. So yeah, this is one of the reasons why I really think this feature of D is perhaps one of the best. It's great. All right. So let's move on to the third example, and I'll run through this very quickly because I don't want to take up too much of your time. D has a package, a software package available for it that does clustering, so that you can do some scalability things on server clusters. It's primarily intended for backing up servers. Backing up the processing that goes on inside servers. So if you need to scale a server sideways, like HTTP servers or whatever it happens to be, then there's a little more involved than plugging 15 machines together and letting them all rip. You need some backing infrastructure to try and tie all these pieces together. And it doesn't matter whether that's cached things that are lying out on multiple boxes. It doesn't matter whether there's some external processing going on. There just needs to be some kind of infrastructure there to help you get where you want to be. And that's what this clustering model is about, what this package is about. What the model exposes is a set of services. And those services are called queue, cache, bulletin, and task. And queue, you'll probably all be familiar with. Anybody here, how many people here have used publish subscribe before? Anyway, okay, yeah, a whole bunch of you. Great. It's all right. So queues are a little like publish subscribe. In fact, they're very like publish subscribe. You stuff something into the queue, and then later on you can pull it back out. It's a persistent storage. In this case, it's a distributed persistent storage. Cache is similar. Have you guys heard of memcached? Sure you have, right? Cache is similar to memcached. It's a transient storage that's useful for stuffing things out and getting them back quickly. It's faster than queue, and that's really the distinction between the two. The other distinction, of course, queue, you will get back the last thing that was put in, and cache, of course, is keyed. It's a distributed hash table. Task is a little like an RPC, in that you can send something out to be executed on a remote machine. So if you have a cluster of machines out in the background, and you have a whole bunch of, if you have some kind of a process that you can break up into discrete parts, you can just toss them all out into the cluster, and then they'll come back again once they've been processed. So it's a little bit like grid processing, but no, not really. And then there's this thing at the bottom called bulletin. And bulletin is like a shotgun message. It's like, hey, everybody, get a load of this. It can be used for heartbeat, or it can be used for whatever. The notion is that you send a message out once, and it goes to everybody, gets dispersed to everybody. The model itself is synchronous and asynchronous. So you can ask the cluster for pieces directly, synchronously, and wait for them to come back. Or you can register interest in something and say, hey, if something happens to that queue over there, then let me know. And you'll get an asynchronous callback. The other thing to mention about the model is that it's all based on what is called a channel. And all the channel is just a name that allows you to partition the cluster into as many different pieces as you want. So a channel is very much like a pub/sub name. With pub/sub, you have a topic, right? And you publish to a topic, and you register interest in a topic, and the topic is usually, some structured name, slashes or dots or something in it. The channel is exactly the same way. So all of this operates on a structured sort of partitioned channel basis. And that's the general idea. And then you get a bunch of clients that sit around outside the model, and they make requests on it. Now, of course, the interesting thing is this is just a model. There's no implementation behind it, per se. So you can implement it as you can go out and buy, like a MQ series from IBM or whatever, and build a wrapper around that to make it all work the same. Or you can, whatever, you purchase bits and pieces. If transactional integrity is really, really important, is the most important thing for you in your application or your approach, then you can go out and grab the appropriate piece of software and very simply map this type of model onto it. Of course, you don't have to map the model onto it at all, but it would be convenient for the rest of the D community if somebody did that. There is one default implementation, which I'll talk about in a minute, and that's called Tina. So hence the clustering with Tina. Some of the things that the model, actually the verbs that the model actually provides for you are all listed up there. This is all of them, basically. On a queue, you can do a put, and you send it a message, and you can do a get, and you'll get a message back. Same with cache, but there's a key involved. And with a get, there's an option to remove. So it's basically put, remove, and get, tied into a couple of functions. With bulletin, you broadcast messages. And with tasks, you execute messages. And all of these messages are actually D objects. So you can imagine that they're serialized at some point and squirted out onto the wire and so on and so forth. But so that's the way it works. So it is specifically for the D language. It is not an intra-language or interlanguage, I should say, communication system like dbus, for example. It's not intended for that. It needs, each of the clients that sit around the model are expected to be written in D because there's D objects. There's no reason it couldn't be extended, but I'm not sure that there's much point. This one is very specific to the D language. All right, so just a few notes about Tina. There's no single points of failure, and that's important to some people. That's because it's a pure peer-to-peer design. You start up a few queue servers on a bunch of machines. You start up a few cache servers. You start up task servers in whatever mix and match that you want, and then you let loose your applications on the same network. And in fact, Tina is designed specifically for a LAN, not a WAN. And for bulletins, for example, the shotgun message that you go out, that you can send out, it actually uses UDP multicast for that. So it will not work on the Tina implementation will not work on a LAN, primarily because multicast hops are usually turned off on a LAN. So anyway, that's the general idea. But the point is that the implementation for Tina has nearly zero GC activity going on because it uses slices. Big surprise there, right? And the currency, of course, that it uses is serialized D objects. And I'll try to demonstrate some of that going here. All right, for a storage request, let's suppose we're doing a get, and we're hitting the queue. So the client makes a request, a get request on a channel, and the request goes out here. The request gets buffered up on this side, goes through some server in the cluster, one of the peers out there. It hits its little local storage, drags an entry, a serialized D object out of there, straight into the buffer, squirts it back over the line into another buffer on the client side. That message is deserialized or thawed or unfermented, or however you want to describe it, gets turned back into a D object at that point and handed to the client. Now, I'm sure some people in the audience here might, at this point, be going, well, wait a minute. You've just given me back an object with references to something that can actually go away. Well, yeah, actually, that is the case. This is another case of the fast path at work. When you do a get, for example, on a cluster. Most of the time, you're just interested in the content right there and then. You're going to do something with it, you're going to deal with it, and you're going to move on. It's gone, right? Go on to the next thing. Right? Sometimes you want to get something back from the cluster, and you want to hang on to it. So the classic example would be an L1, L2 level cache, whereby the L2 cache is actually the cluster itself, and the L1 cache is local to the machine. When I grab an entry from the remote cache and pull it back, I now have a D object in my hand that turned up from the cluster, probably got there from some other machine, and I want to stick it in a local cache so that the next time somebody asks for that, I actually have it locally and I don't have to go out and hit the cluster. Of course, I need to have a more permanent or less temporary copy of my object at that point. So at that point, I would actually duplicate the message object. And the messages, the D message, the base class actually has a function on it that you can override to do that to your desire. Right? So we have a fast path through the system whereby you'll get it back and it will be sliced appropriately. Oh, the only things that are sliced, of course, are arrays. Things like ints and floats and da-da-da-da, they're all just copied, of course. It's just arrays. All right, and on a put, you're going to put something, then, of course, the client gives a D object here. It gets serialized into a buffer, squirted over the wire, gets buffered on this side, and the buffer itself, you just take the buffer, toss it into storage, and the same on the way back up. You just take the thing out of storage, shove it back over the wire, and there's just very little processing going on inside there. One of the more interesting ones is a task request. Task request is a little bit like a bulletin dispatch. Let's talk about bulletin first. So if I'm a client and I want to send a heartbeat to everybody in the entire cluster, all the clients, all the servers, everybody, on a specific channel of interest, then I have the bulletin message is actually a D object. It gets serialized down here. It gets sent out UDP multicast shotgun fashion to everybody in the entire cluster. And then as it arrives on the client, it gets deserialized and given to a listener. Right? So you get a round trip going from client to client at that point, or from server to client, or whatever it happens to be. The more interesting one is the task request, and this is an executable piece of code. It is a D class that can be executed remotely, and you stuff all your attributes and so on inside the class, and you toss it out into the cluster, and it comes back in. Great, and you've got your results inside that class as well. Everything is contained within the class. In fact, with a task, you can also store it in a queue. So if you want to decouple the execution, remote execution of processing, you can take your tasks, which are class entities, with all their arguments inside as attributes, toss it in a queue, and then there's some other client out there which is going, oh, I'm free, give me queue entries. And it takes the queue entry and it executes it. And then it sends it back into the queue. And from there, the queue will get back to the original client. At least that's the idea. So you can do, with tasks, you can do synchronized execution, and you can do decoupled asynchronous execution. Anyway, so the interesting part with tasks is that it gets squirted across the wire, it gets serialized here, squirted over the wire, gets deserialized on the task server. This is a synchronous execution. And the task server goes execute inside the object. It then serializes it again into the buffer, squirted back over here, deserialized, and given back to the client. And the results are in there. In the TINA implementation, and this is not necessarily true of any other implementation, in the TINA implementation, all of that happens without a single memory allocation. And it's all done through slicing. This is good stuff. If you want to operate this way, you can do it in D very, very easily. All right. Yes?
First question. You've got a slice to an existing array. Does that prevent that array from being grouped?
Yes.
That's good.
Yes.
So you were talking about persistence of the original
Right.
data. You've got an object which is populated with slices into that array. That array is not going to go away as long as that object exists.
Yes.
Second question.
Oh, that's the way it operates. Yes.
A minute ago you mentioned if you wanted to keep the object around, you would do it, and it would build all its structure. Would it not be easier to just ask the system to abandon the buffer and not create or not reuse it rather, and allocate a new buffer that way you don't want to copy anything?
Good point. Yes, that would be a good way to do it too. Yes.
Similar question about locks. If you lock the main array and slice it, you have to be the same lock. Or if you synchronize on the whole array, so because you're making some little change, are the slices automatically prevented, or they also?
That's a good question. Walter?
Slices don't have blocks. You don't have to create a block from slot.
Right.
Class objects have blocks. No other objects. Arrays do not have blocks. And there's a good reason for it. If you slice it away, where's your lock?
Yeah, that's, I think.
Okay. Let's
Okay, so the upshot of all of this that I should mention before I move on is that I like to do a bit of empirical testing now and again. And one of the things I did was create a bunch of clients, like I was doing with the introductory story. We created a bunch of clients and we beat the crap out of some poor server to see how many requests a second it would do. I tend to do a similar sort of thing with these kind of servers also. This particular one, I ran on the order of about 1 billion requests through it over an extended period of time. And the interesting thing about it, I did this on Windows, and with Windows you have the process manager or whatever, right? You can take a look, task manager, you can take a look to see what things are doing, how much memory they're using, how many handles, da-da-da-da. Well, the interesting thing is that in the case of the queue and the task and the whatever, not cache, but the other guys, the other servers, they start up and they use like 2 megabytes of memory. Right? It's a tiny little thing. Right? 1 billion requests later, it's still 2 megabytes of memory. And this is good. It means there's very little activity going on inside the heap. And it means it's running fast, it's running very effectively and very efficiently. That may not be a priority for your application, but if it is, D has an answer. All right. So how does this all tie in with Tango? Tango is a library that implements some of these notions at various levels, particularly in the text processing arena. The for each, the line parsing example, it does that sort of thing. The integer conversion, and that sort of notion. It gives you the opportunity to pass in an output buffer, and if you don't, then it does what it does. But it's using slicing all the way through there, so it returns a slice of whatever you pass in or don't. Lots of different utilities and tokenizing and so on. And the I/O subsystem in Tango also has fairly extensive support for slicing in buffering and various readers. And readers are things that decode from serialized streams. Readers and writers are protocol handlers, if you like, and they understand about slicing too. Okay. All right, so quickly a wrap up here. I'm going to repeat what was on the first slide. Overt GC reliance still has the potential to make any language or system appear sluggish. That is true with D, as it is with any other language that has a garbage collector. Obviously, D has a nice feature in array slicing that can help you avoid putting too much pressure on the garbage collector. Don't get me wrong, I think the GC is a fantastic tool. It's great. It's just there's really no reason at all why libraries in D shouldn't be lightweight in terms of the heap usage and so on. Yeah, there'll be plenty of libraries that allocate 1 gigabyte of memory to do some intensive image processing or something like that. But run-of-the-mill libraries that really shouldn't need it. And the real upshot there is that whatever language you're using, whatever system you're using, you should really show the GC some love. It's a tool there to be respected. And unfortunately, with Java, you don't have many choices, at least not mainstream choices, that are easy to use, that are built into the language, like struct and array slicing and so on, or classes allocated on the heap. And from there, I think, yes, that is all. Thank you very much.